All right, we're in section 9.3 where we're being able to identify special products of polynomials. Now, like I talked about in class, this is sort of an extension of multiplying polynomials, where in some cases we have special patterns that we can detect, and we can, instead of foiling out the patterns, we can, or foiling out the binomials, we can use these patterns in order to solve them. You're going to get the same solution. So it's just a matter of your preference in how you solve. So today, first two examples I'm going to show you are what is called square of binomial patterns. One of which is, say, if we had two values a plus b and we squared both those values, that would end up equaling a squared plus 2ab plus b squared. If I had a minus b quantity squared, it would equal a squared minus 2ab plus b squared. Now, where we come up with those things is actually what it comes from being able to FOIL out and factor out those products. So one thing you have to keep in mind is, like, if you say if I had something like 5 squared. Now we know that's 25, but it can also be rewritten as 5 times 5. Same thing goes for these binomials as well. So a plus b quantity squared can be written as a plus b times quantity a plus b. This and that mean the exact same thing. And from this, if we can FOIL this out, and it'll equal that. So let me show you. So I'm going to go a times a, which gives me a squared. Then I'm going to go plus a times b. Then I'm going to go here, and that's plus a times b. And then the last one is plus b squared. And since these are like terms, I get a squared plus 2ab plus b squared, which is what that equals. So that's where that formula comes from. And it's very similar to here. I can rewrite this as a minus b times quantity a minus b. So here I have x plus a quantity squared, which in some cases it would be a here would equal x, and b here would equal a. So if I were to use the pattern here, I could say that it's x squared plus 2 times x times 8 plus 8 squared. And then I can say x squared plus 16x plus 64. So then that would be my answer factored out. If I were to say have 2x minus 7 quantity squared, I could say that a in this case would equal 2x, and b in this case would equal 7. So I would just apply this equation towards this expression. So I would have 2x squared minus 2 times 2x times 7 plus 7 squared. 2x squared will give me 4x squared minus 2 times 2 is, that'll be 4x. 4x plus 7 will be what, 28x plus 49. Again, you can still use the FOIL method. So if like I had 2x minus 7 times 2x minus 7, I could go multiply here. I would go 4x squared. Here I'd have minus 14x. Here I would have minus 14x. And then here I would have plus 49. So I got 4x squared. I got like terms here. Minus 28x plus 49. See, these two are the exact same thing. Two different ways of solving it, still getting the same solution. Again, it's just how you prefer to solve these different expressions. So here, For this first one, I'm going to use A equaling 3h, and then my B equals 5. So when I plug this in, I'm going to go 3h quantity squared minus 2 times 3h times 5 plus 5 squared. So here I would get 9h squared minus 6 times 3h, which gives me 2 times 3h gives me 6h. 6h times 5 will give me 30h plus 25. Okay? This one here, for B, I will FOIL it out. So I got negative n times negative n, which gives me positive n squared. Negative n times 3 will give me negative 3n. This here will give me also negative 3n. And this one will give me plus 9. So I can get 9 squared minus 6n plus 9. C is the difference, is the sum and difference formula. So that means that this one would ends up equaling a squared minus b squared. Well, a equals 5k and b equals 2. So then I can write this as 25k squared minus 4. And then the last one, I will use FOIL again and rewrite it. So now I can say it's g squared minus 3fg minus 3fg plus 9f squared. I got like terms here, so it's g squared minus 6gf plus 9f squared. Okay. Last problem I have here deals with what is called Punnett squares. And this is taken right out of your book. It's problem 43 on page 573. And it says that during the 2004 regular season, the San Diego Chargers quarterback Drew Brees completed 65.5% of the passes he attempted. The area model shows the possible outcomes of 2 attempt passes. Now, if you look at this here, I have different combinations of ways that he could have had results of the passes, two of which could have been completed, two of which could have been incompleted. One could have been complete, one incomplete, and the other one could have been incomplete and the other one complete. So if you were to add up these values here, you would end up getting 100%. And 100% in numerical terms is 1. So what I have here is a 1 by 1 square. So for part A, they want us to find what percent of the possible outcomes of 2 attempt passes results in Drew Brees throwing at least 1 complete pass, and explain how we found the answer using this model. So if you look at these, this broken down into fourths, 3 of the 4 categories have him completing at least 1 pass. There's the 4th one that has 2 incomplete passes. So we don't need to pay attention to the 2 incomplete passes, because all we're looking for is the percentage of him being able to throw at least 1 complete pass. So we've said that this square is 1. But now let's break it off into these 4 sub-rectangles, as you can say. And I want to find the areas of these 3, because these 3 are going to help us find the percentage of him throwing at least 1 complete pass with 2 attempts. So here I have dimensions of 0.655 and by 0.655. So if I take the area formula of that, multiply those together, I get roughly 0.429. Okay? Now here I have a distance of 0.345, and then again the distance here is 0.655. So when I multiply those two values together, I get 0.226. And I actually get 0.226 here because it has the same dimensions. So now what I'm going to do is I'm going to add these three values together, and it's going to tell me that the percentage is going to be about 0.881, which equals 88.1%. So he has an 88.1% chance of completing at least one pass, being able to throw it with 2 attempts. Now B, they want you to use a polynomial model to give you the possible results of 2 pass attempts. So a polynomial model would be this. You realize that this entire thing is a square, and we've been working with A plus B quantity squares. So A will be kind of what the representation of percentage of completed passes, and B is going to show the representation of incomplete passes. So what I can do is this, is I'm going to rewrite this as completion passes, which will be in decimal form as 0.655, and I'm going to represent it as C as completions, plus the rest of it will be 0.345I, which I'll represent as incompletions, and that'll be quantity squared. Now what we can do is we can factor this out in order to find our products for this particular expression. So I can use the formula of saying like 0.655 quantity squared plus 2 times A, which is 0.655C. There's a C here, I apologize. Times 0.345I plus 0.345I quantity squared. So here, if I were to square this here, I would get 0.429 C squared plus, now if I multiply this out, I would get 0.452 CI plus, now if I multiply this out, or at least I just take the square of it, I would get 0.119 I squared. And then that would be my representation of using polynomials. And that is being able to use special products and use different patterns in order to solve products of polynomials. Hope this helps. Till next time.